that is your related to the civil engineering. I told you before that we will cover we will try to cover the numerical that is related to your core engineering. So it is one of them. Let's read out the question. It is a numerical 1.53 from the book of Sangil. The basic barometer can be used to measure the height of the building. We have seen the barometer in the last lecture. We can also let's end the slide here and go into this is barometer. Okay, this is barometer. In the last lecture we already studied that barometer is used to calculate atmospheric pressure of air. So you can see when when the atmospheric pressure high, that pressure exert this bottom water and that pull the water up in above the this tube, which gives the reading of height, and that can be converted into the pressure by the simple formula is equal to P is equal to rho gh. And when this height gets lower, it's easy when the outside of atmospheric pressure is lower, these heights also decrease and allowing more air into the bottom level. So by this variation of the level we can calculate the atmospheric pressure. And I also told that there's a air standard index which shows uh, air pressure at different altitudes. So when we are in planes etc, we know that the plane is flying on that 30,000 foot height and 20,000 foot height. We can get the pressure from the ASI, or and from the pressure we can calculate the height of the plane. Let's say if the barometer of the plane shows reading of 0.87 atmospheric, so we can correlate this pressure with the ASI index and get the height of the plane. So in this way barometer can also be used to measure the height of the plane or building etc. This is the graph of ASI index, that is table A16, that is also in the thermodynamics and engineering approach Sangil book. You can go and see the table over here too. So this is altitude and temperature and pressure. So when the if in the plane their gauge pressure showing reading of 85.6 kilopascal, so we can easily relate the plane height, that is 1400 meter altitude. So in this way the plane calculated its height. And in this particular numerical we are calculating the height of the building. Simply how the basic barometer can be used to measure the height of the building. If the barometer readings at the top and the bottom building are 730 and 755 millimeter Hg, that is a tube level as shown in the figure. In the top of the building the reading is 730, and the bottom top and the bottom reading is 755. So definitely on the top the water level uh, the atmospheric pressure is lower, so more water comes here and the reading is 730. When we set in the bottom, the air pressure is more, so it's exert water here, so water level goes down and the level now then gain to 755 respectively. Determine the height of the building. Take the density of air and mercury to be 1.18 kg per meter cube and 13600 kg per meter cube respectively. So in this tube the fluid is mercury, that's why the level millimeter is giving with the reference of Hg. Hg is unit of mercury. Now first we will calculate the pressure at the top, P top, simple by formula OGH. The density is 13,600 multiply by 9.8 multiply by 730 top. We are calculating 730 millimeters means 0.730. 730 divided by 1000 give 0.730 because it is in the millimeter reading. We have to calculate the height in the meter quantity. So it's P top. We get the reading of P top. Now calculating this, we get the answer 97.3 kilopascal. This reading shows Pascal, then we convert this reading with the 1000 to get in kilopascal. Now we have to calculate the pressure at the bottom. For bottom, we just only need to change the height. We just only change the height from 0.730 to 0.750, 755, sorry. And then we get the answer P bottom 100.7 kilopascal. Next, come to the next slide. We need to make spaces like this. Now we get two readings. Now we have P top, that is 97.3 kilopascal, and P bottom 100.7 kilopascal. Then comparing to this reading, we get actually the height. Consider this is the building, this is the pressure of air, and this is the pressure of air. We get the top 97 and bottom is this. So in this pressure is exerting by this column of air. So the pressure at the difference of pressure, W weight of air divided by its area is pressure of air into the bottom. It is simply P of bottom minus P of top. So this pressure, we can formulate this pressure into the rho GH of air in P bottom, that is 100.7 minus. So the difference of this two reading is due to the height. So these difference gives the height of building. Because it is due to the height of the building, the difference of air pressure is due to the height of the building. So we just simply minus this reading and get the height by simple converting this pressure, difference of pressure, into the rho GH formula, and from this formula we get the height of the building, 97.3 kilopascal. then simple this mobile is making problems in the slides. Anyway, we get raw GH of air is equal to 100.7 minus 97.3. So this minus 3.34 kilopascal, and P raw GH is 1.18 as shown the density of air, multiply by 9.8 multiply by height. Now we get the height. We convert in kilopascal into pascal because to get the height in the meter. So 3.34 multiply by 10 to the power 3 multiply by 1.18 multiply by 9.8, we get the height of 288 meter. So the height of the building, which approximately is equal to 288. Okay, we can get the height of the building by this formulation. Also, the second method I told you that you can also correlate the height with the different pressure by simple calculating the pressure at that height by using this graph. But definitely it will not give the accurate reading because there is a difference of 200 in the reading, that reading of 0, 200, 400. So if you want to calculate from this chart, you have to make correlation between two readings. So if you want to calculate accurate, you can calculate by this formulation, whether in the plane or any instrument. You can drive the equations coming from pressure readings into the height reading. Now these are the two numerical of today class. Now comes towards the further topic of the subject. One simple definition we left in thermodynamics is temperature. By definition, it's very simple: degree of hotness or coldness, also defined as a average kinetic energy of molecules. The zeroth law of thermodynamics states that if two bodies are in the thermal equilibrium with the third body, they are also in a thermal equilibrium with each other. So we can, it's a very simple law. So we form the thermodynamics is called to be zeroth law of thermodynamics. So basically we will cover three laws of thermodynamics: zero law, then after that slide we have first law of thermodynamics, then second law of thermodynamics. So by this definition you can correlate that replacing the third body with the thermometer, the zeroth law can be stated as two bodies are in thermal equilibrium if both have the same temperature reading, even if they are not in contact. Let's make three bodies: body A, body B, and body C. Yes, to understand zeroth law of thermodynamics, let's make three objects A, B, C. If these two bodies are in contact, and even though they have different temperature like 10 or it has 5 degree, so it transferred the net heat transfer from 10 to 5, because heat transfer flow from high temperature to low temperature, and now it's become temperature both this body A decrease the temperature and B increase, so it both comes the temperature, let's say 8 degrees centigrade. Now they are called to be in thermodynamics. These two bodies are in thermodynamical equilibrium. But if body A, let's suppose if body B is replaced by body C, and body C has 8 degree centigrade, so then body A and C are called to be in thermal equilibrium because it is not transfer any heat from either any point. So but body B are not contact with the C. Body A contact with B and C, but body B is not contact with body C. But due to the same temperature, we can say we can call them to be in thermal equilibrium. This is the zeroth law of thermodynamics. If temperature is same and no heat transfer exchange between two bodies, even it is not in the contact, then it is also said to be in thermodynamical equilibrium. These are the statement of zeroth law of thermodynamics. Let's recall them again and then you can easily understand. It states that if two bodies are in thermal equilibrium with third body, they are also in thermal equilibrium with each other. So all these bodies are in thermal equilibrium with each other. Replacing the third body with the thermometer, zeroth law can be restated as two bodies are in thermal equilibrium if both have the same temperature reading, even if they are not in contact. So body B and C are not in contact, but still they have in same thermal equilibrium. Why it is called to be zeroth law of thermodynamics? Because physicists and engineers works on first law of thermodynamics, that is said to be energy can neither be created nor be destroyed but converts from one form to another. So after realizing first law of thermodynamics, they realized that it is more fundamental than first law of thermodynamics, because all the thermodynamics relates in the heat transfer and in the thermal equilibrium of the body. So they called this law to be zeroth law of thermodynamics. Let's move on. We have different temperature scale. Temperature scales enable us to use common for a temperature measure, common base for the temperature measurements. Based on freezing and boiling point of water, we have Celsius scale, Fahrenheit, Kelvin and Rankine scale. So we know that the degree centigrade and Fahrenheit, their absolute is the degree centigrade absolute scale is Kelvin. You can see from this that 0 degree centigrade is equal to 273 Kelvin, and minus 273 is 0 Kelvin. So Kelvin is a absolute scale of degree centigrade. And for Fahrenheit, you can see that 32 Fahrenheit is equal to 491 Rankine, and 0 Rankine is minus 1459.67. So the absolute scale of Fahrenheit is Rankine. This might be new scale for you, because in first year and second year we only study degree centigrade, Fahrenheit and Kelvin. So these are different scales of temperature. Now comes towards the form of energy, that is also related to the first law of thermodynamics. Energy can exist in numerous forms such as thermal, mechanical, kinetic, potential, electrical, magnetic, chemical and nuclear. The sum of all form of energy is known as total energy of the system, denoted by capital E. The total energy of the system on a unit mass basis denoted by small e. Like if we divide this energy with total mass of the system in the kgs, so this donates to be small e. In thermodynamic analysis, the total energy generally is divided into two groups: microscopic form of energy and macroscopic form of energy. These are the different form of energy. I just placed this figure before this slide, so you can understand that form of energy that is mainly there are two: kinetic energy, energy of a movement, and potential energy, stored energy. In kinetic energy we have a thermal energy, mechanical energy, electrical, magnetic, and the potential energy we have chemical energy, that like petrol. It has potential to produce lot of heat by burning this chemical, or by making combustion of the chemical. So it is a potential energy. Elastic energy, like spring, if we store the force in the spring, we can reclaim the force, we can reclaim that energy in any time. um, Elastic energy, so we stored this energy. Anything which has a restoring factor, that is a potential energy. So in elastic body we stored the energy and utilize whenever needed. In nuclear energy is also form of potential energy. In the nuclear we make fission and fusion reaction and to produce lot of energy. Gravitational pull is also a potential energy. You in first year, second year, you already solve the numerical related to the potential energy. If the ball throws above some height, it has potential energy at that height, like 10 meter, but when it going toward the down, the potential energy convert into kinetic, and when it finally when it hit the body, all the potential energy convert into the kinetic energy to apply that pretty much force on the ground where it hits the ball or any object. So we have two form of energy: macroscopic form of energy and microscopic form of energy. A system poses as a whole with respect to some outside reference frame such as kinetic or potential energy is macroscopic form of energy. Like you are visualizing this energy, like shown in the car. If the car is speeding at some elevated height, when it goes at the top of the height, it gain all the kinetic energy into the potential energy. And when the car turn off the engine and then goes down from that height level, then this kinetic energy that convert into the potential energy by gaining height converts into the again into the kinetic energy by moving this car. So it is a conversion of kinetic into potential and then potential into kinetic. So these are the macroscopic form of energy. It easily visualizes in our system. And we have another type, that is microscopic forms. Not this is not a type, this is a form. Sorry, I just correct myself. This is not a type of energy, this is a forms of energy. Microscopic forms, those related to the molecular structure of the system and degree of molecular activity. They are independent of outside reference frame. Besides this microscopic, it is independent of reference. In the previous form of energy, microscopic, we have a frame of reference, like just like in previous form of energy, the frame of reference is very important. Like this car is traveling at, let's suppose, covered distance of covers the height of 20 meter. So here it is 0 meter, this is 20 meter. So from the frame of reference we are calculating the height, and then this height is the gaining of height and the potential energy utilizes to form again the kinetic energy. So frame of reference is important to calculate the energy. But in the but unlike microscopic, in microscopic the frame of reference is not necessary. It is they are independent of frame of reference. Like molecular translation, if covers different height, doesn't matter. Molecular rotation, electron translation, molecular vibration, they are all independent of frame of reference. So we stop our lecture here. In the next week lecture we cover more more topics of thermodynamics and solve the numericals, inshallah. Till then, take care. See you then. Khuda Hafiz.